Kick it off.
I'm not. I'm so like ready to be out of this class. But you know, it's that time of the.
To say that aloud.
I'll say that aloud.
I'm so over you guys right now.
No, you know how it goes. I bet you feel this way too. It's 9:30. It's Friday. It's freaking sunny outside, although it's a little chilly. You know, it's just we have better things to do than this, right?
We've put in our time already.
Bays is Bay, all right, but I'm not even going to check that the stream is working. But if you're on the internet and you don't hear this, so I'm sorry. Anyway, not that that would matter. Why aren't you in class at Iowa if you're on the internet? I thought our program is deciding like things on how to make us more attractive to the outside. I think I'm just going to like tout our program on the internet in these classes.
Yeah.
Imagine how, if you think this class is awesome, imagine how awesome it is outside of class. After class, we all cuss a lot. Anyway. Let's start with Ben. We had a request from Ben for code from last time. That means I need to remember last time. That was like a week ago. Gosh.
Almost exactly.
Almost exactly a week ago. All right. Let's get some code out here. We want to look at the multidimensional IRT code.
Yeah, specifically where we started specifying priors for the factor.
Yeah. Let's see if I can get down there. Model 2. Actually, let's just look at my chunks here. 3 parameter. Nope, that's not it. Multidimensional IRT. Okay.
All right. So.
Right.
Yeah.
Yeah, right here.
So we, in general, have. It's not there anymore. Okay.
Did I do something wrong?
No. And maybe I saw it in the CFA. Anyway.
Yeah.
Anyway, we've got some indeterminacies we need to deal with.
Yes.
Specifically, location and scale.
That's right. We need to figure out the location of the latent variable, the scale of the latent variable.
And also orientation latent variable, right?
Yes. Direction where the location and scale happens to be. That's right. There's multimodality that show up in some of these algorithms.
What I thought I saw either in this or the CFA was when you're defining the distribution of theta, you said it was inheriting variance from the marker item, but we specified it to be
part of the variance.
Sure.
Yeah.
Sure. But we specified it to be multivariate normal 0, 1.
Theta?
Yeah.
Oh, that shouldn't have been the case.
Yeah, that's why I was confused.
Yeah, no. So if you have a marker item and you fix the variance to 1 on theta's prior, that's an artificial like constraint that you don't want to do.
Because here we said theta is multivariate normal with some mean vector and some, in this case, inverse covariance matrix.
That's right. The inverse covariance matrix we're going to sample from a Wishart distribution, and the mean vector we're just going to fix to 0 here.
So we say it's 0, and do we go down and specify?
Here's the covariance part right here, but then here's where we fix our anchor items, marker items.
Can you go up a little bit more for me?
Yeah.
So inverse B is Wishart. Theta inverse. Yeah, so where is theta dot incov dot 0?
Let's take a look here. Inverse phi theta incov dot 0. I'm going to put that as a piece of data I send into.
Yeah.
There we go. Yeah, and it's just going to be a diagonal matrix.
Sure.
And I was trying to do that to make it so that I'm putting as little weight on the covariances as possible.
Yep. Okay.
But
yeah. I think I'm good.
Okay, cool. Yeah, if I did that, if I had a 1 there,
right,
that's a copy paste error.
Sure.
And a lack of attention on my part. So.
Because you would have identified it twice.
That's not a good idea. Or artificially constrain one of the variances to be smaller. Actually, we pumped up the variance probably in the unique variance of well, I guess it could go either way, but yeah, for the first item. Let's see here. Let's do some class housekeeping notes. Most of you should receive homework 3 at grade and homework 2, and things are going well. What did you think of your articles that you found for this time? Not much, right? Like the standard for publishing in Bayes is woefully inadequate, right? You think about what you're doing to make a model work, and then what's going on otherwise. Ooh, that's tough, right? So, how confident do you feel in your ability to do some of the Bayes work outside of class? Like if you want to if you think of a brand new model for your dissertation, can you code it? Do you think you can do that?
It'd take me a while, but I think I could get there.
That's fine. Taking a while is good. Not an infinite amount of time, but something that would give you a fighting chance, and then better yet, trying things out and then sending them off to get help. Yeah.
It depends.
Depends.
From my end, if I want to go from this to start adding random effects,
Yeah.
I'm not sure how to do that from here to random effects.
Well,
The funny part is that I know how to do random effects outside of this,
that's right.
but I don't know how to put the two together yet.
Well, this is where we have a couple weeks left of class. I'm asking this question now because I sort of have a schedule where we're going to get through latent class analysis, but then we get into like Bayesian inference networks. But effectively, we've already seen that. It's just complicated graph structures here. It's just piling it on. And we can go into that. That'd be fine. But if you want to throw an example, if I want me to throw an example for random effects in, I got it. I'll get some of Lisa Hoffman's code, Lisa Hoffman's data from her book, and try to do an example.
And maybe obvious, and I'm just not thinking straight because I have done random effects in the past under the Bayesian framework, but I haven't done anything with what was numerical variables, not with dichotomous or binary. So
Yeah.
So it may be just tweaking what I already have done, and I'm not making it.
So you've done random effects in the regular linear regression on with Bayes.
With Bayes.
Yeah. Then it should be a matter of flipping feeling to burn, as we said last week, right? Flipping the distribution of data. Like when you're talking about your data here, X goes into Bernoulli rather than.
So it's just tweaking the distribution.
That's right. That's exactly it. And if you have a core of code from before, I mean, there are subtle differences, and usually it's with features of models like identification or ranges of variables. One of the things in IRT that we found was it's a lot easier to specify a smaller variance for the item parameters, and that was because on a logit or in a probit, the range of y is truncated, is set to be a very small number compared to in the regular real data, it can be anything. And so when those parameters are basically standard deviations of y per standard deviation of x, well, x itself may be latent and that standard deviation may be even fixed. And then y has a smaller range, so you can get by with this relatively, the ratio of prior to range of expected variable is really the issue there. So, is that? So,
See, I'm not seeing clearly. I'm not seeing.
no, it's okay. It's Friday morning and it's sunny outside. What about the rest of you? So Dr. Alloway says this. Ben says it may take a while. What about you? If I made homework, the last homework, a fun with models homework, and I give you a model that you've never seen before as a test to try to code it, would that be an exercise that you want to try? I mean, again, you know how it works. I'm not.
Trying to make them cry.
No, I'm not going to grade them harshly. In fact, all of your grades up to the minute are on Icon right now. And by the time the last homework gets assigned, I'm guessing you're already going to have an A in this class. So this is more like I'm wanting to challenge them. I think you're all exceptional people, and I just want to give you something where you have the chance to have some interaction with me before you head out and do whatever with this later on. Would that be an okay thing to try?
No.
I could make it individualized. Everyone's get something different. Or I can get like a Form A, Form B. And then when you work together, you have to help on each other. Form A can only work with a Form B.
I think you're making it worse.
Are you getting nervous about it? I don't want to. You don't like the feel. You're not going to fail the class.
Mostly it's for me personally. Like it sounds like a fun thing to do, anything I want to do. I do think it'll be extremely time consuming.
Well, I don't want it to take too much time.
Sure.
But if I put a model on there, I talked about unfolding model. I'm trying to think of things. If I put an unfolding model on there, or something along those lines, or better yet, here's a paper that had a model in it. And here's some data. Try to recreate this model with these data, something like that. Would that be Would that be a valuable exercise? Not that the time consuming, but that was it. That's all there was to homework. You don't have to look up an article. You don't have to do anything. That's it, making this analysis. Would that be something that would be of value to you? Maybe. The balance of value versus time. I get it.
For me personally, I've enjoyed what we've been doing is taking models that are more or less familiar to us and showing us the Bayesian approach, which, as you said, makes us, I think, understand the models better. And since we already know the models more or less, it makes understanding the Bayesian part more manageable.
That's what I was hoping. Once we got into the models,
right?
I was hoping it would be that sort of a multiplier. Eventually, you get to learn about a little bit of each.
But if you're introducing theoretically a model we're less familiar with,
it's going to still be close to the same family.
Sure.
It could be like maybe we have a structural equation style model. Path model with latent variables. One of them is an IRT. You have a measurement model. It's Bernoulli. You may have a classification variable in the middle, which we're going to learn about next week, and maybe you'll have something else on the out. Something along the. It's still the same class. It's just now piled up. What I'm trying to do with that exercise is this. I've always found the hardest part of Bayes. Once you get to a certain level of Bayes, which I'm hoping you're getting there because you're understanding concepts of prior and posterior and choices of kind of selection of ways of doing things, then the hardest part becomes, hey, I've got this idea for a model. What's the likelihood function for it, right? And I want you to have a chance to sort of play with that in your mind a little bit. What's the likelihood function for this? Because if you unlock the likelihood function, you can do it. The priors, yeah, you can pick priors, you can change it, you can guess and check priors all you want. It doesn't make a difference, but it's never going to work unless you get the likelihood function, right?
That's useful in both Bayesian sense and ML sense.
Right. If you're going to do anything with a new model, it all starts with what is the model and how do you translate that to likelihood and data. And that's a fundamental skill that I found infinitely useful in my life and in career. And I know that it shows up from time to time, but where it also helps me a lot is when someone says, I got this new way of doing stuff. Like at my core, what do I do in my head? Translate to likelihood. When I translate to likelihood, now all of a sudden I know a number of these likelihoods. Right? After you do a number of these, if you do your dissertation or you do another project, you'll know a likelihood. You'll know a number of them. Then the next thing comes along and then it's like, oh, look, it's amazing. Translate it to likelihood. Oh, it looks like this. All right, never mind. Right? Or the other way. Oh, actually, I've never seen this before. This is really considerably amazing. So other ways of looking at it. All right, I'm just trying to, one of my objectives in this class is to not just turn you out to be people who can repeat analyses we can do in ML. Really, I want you to take the ability to be creative with science and do things well. It's that conversation from the beginning of class. Would we have taught ANOVA the way we did with homogeneity of variance if we had ability to do models that were heterogeneous from the beginning? My answer, I don't think so, right? But why do we do it now? Because that happened before and we have to be consistent. What's that? Traditions. That's the way.
It's like the story with the ham and the pan. Do you know that story?
Do enlighten us.
Okay, so there was like a woman was cooking a ham and then she cut off the end of it, and her kid said, "Why did you do that?" She's like, "I don't know. My mom always did that." So she asked her mom, "Why did you do that?" "I don't know. My mom always did that." So she asked Grandma, "Why did you cut the end off?" She's like, "Because it didn't fit in the pan otherwise. It didn't have a big enough pan."
See, I'm hearing this and I'm like, oh, it's going to dry the whole thing out. You need that end to keep the moisture in. or put a pot of water in the oven while you're doing it.
You're following practice without understanding the rationale.
Right.
You don't need to cut the end off, right? We don't need to teach homogeneity of variance.
Exactly. And I sort of get, like with the ham example, it kind of falls apart because it's simple one way or the other. But I can get like jumping into like certain things in ANOVA is hard. So you need a kind of a simplification point to jump into. But then kind of all the little, once you get in there, you're like, all right, but that's not really realistic. Let's go switch this around a little bit. But anyway, I want you to be able to be creative. I want you to be able to push the envelope. if you look at like a mimic model, or you look at, well, that's a bad example. If you've got certain versions of like diff analyses or invariance analyses, we're being on a student's committee. He works at Apple now, at KU, and I remember he was one of his advisors was a fairly well-known IRT person, and he had this model where had he had an interaction between a latent variable and an observed variable, he would have had a full measurement variance style, whatever. And I'm like, why didn't you just do that? It's sort of a brand new model. He's like, well, but no one does that. Yeah, but you could do that, and it's right there. And he's like, but one of the assumptions of the model is that there is not an interaction. That's an assumption. That's a model. That's that model. This model doesn't have that assumption, right? It's like that whole interplay. So what I'm trying to get you to shake from with this class is another meta message. Is like there are certain dogma that we have in the world, and some of those are based in reality. Like I'm a model fit Nazi. When you say that, or no, must fit the data. Right? Sorry, maybe Nazi is not the right term in this day and age. But I pointed it myself, right? Well, maybe that's not good either. I'm not a Nazi with anything. I'm an authoritarian model fitter, or no, I don't know what you'd call me.
You know, my wife tried to teach me to stop digging.
I'm digging. But you know what? You never find gold unless you dig deeper, or oil. Wait, that's not good either. Never mind. Shoot, boxed in. Anyway, there are certain things that I preach dogmatically, but I think that's because I think if you ask why, that there's a real good rationale. What I'm hoping that you learn from this is that you don't have to be dogmatic, and that you control your own assumptions for a lot of what you do.
May I piggyback on that for
Yeah, please.
To me, that is the key. Yes, I don't have issues with people making assumptions that they verified in their model and they have.
Mm-hmm.
Yes, what I have an issue with people making assumptions that they don't verify, and they stay in restricted models that are not really meeting their needs of their data.
Agreed.
Yes. To me, the issue is the assumptions are for being relaxed.
Yeah. Well, here I agree, and I'm gonna go tread very carefully on this here at this institution with the history here. Why did I throw the pen at some scores?
Because you have a model.
Right. What are the assumptions? So, for instance, when you're adding up test items to do what you're going to do, that's a heavy amount of assumptions that you're carrying with you. Probably not a good idea, right? But how many semesters or classes did you take on that for the students in our program?
And why some scores are terrible.
No.
Learning the properties of them.
I'm threatening the hierarchy here. I'm sort of doing that, but I'm trying to break dogma. I'm trying to get you to think outside the box a little bit. There are cases where sum scores may be valid. How does G theory change if it's not a sum score? How does G theory change if you have a heterogeneous variance? These are questions that you can ask. It'd be very interesting to ask.
See,
I feel like I'm walking on hallowed ground.
But here's the catch-22 of that, yes? Even if you go to a mixed model, yes? If you go to the all literature the mixed model, you know, they were derived around F distributions, yes? So they were derived using sum of squares in some way. Yes, the thing about it, even the between groups variance, it can be sought as a subcomponent of the sum of a square error. If you
Okay,
take
I
the
give you that.
quadratic form of the sum of a square error, you will have the between group variance there, and you can derive a poor estimation that is a method of the moment, but you could derive a poor estimation of it. I'm talking before this.
Okay, I was gonna say, because like,
I'm talking about the theory behind this. Yes, the theory go back to the 40s.
oh right, yeah, but I'm talking like,
The estimation precision, I'm with you. But sure, and by the way, we can pick back with the restricted maximum likelihood, because it's more than one version of it, yes? For the MLE, we all agree what the likelihood function looks like. For restricted maximum likelihood, you have competitive competitive forms of the restricted likelihood.
So I'm not familiar with those. What are they?
For instance, what SAS in PROC-IML does is not the same that what LME4 does.
Oh, right. Well, with where they phrase the V matrix.
Yes. So.
But the actual likelihood function is the same.
If you piggyback the literature, not really.
Really?
Have one form, and you can find another competitive form in literature. The one that taught me that was Wolfgang.
And see, I hear you on that, but I thought that there's a connection between the two, and it's easy. It's an easy transformation of variance components. It's correlation and diagonal.
But
yeah.
Attention to that, and we're comparing results with different restricted likelihood. We may be hitting our heads against the wall why they don't converge to this.
But I'm saying if you want, when you get to a mixed model, you have no sums of squares anymore.
Huh?
We're not doing sums of squares anymore. We sort of have the forms of it here,
See,
but
I respectfully disagree with that. We don't use it in practice. Behind all of that, you have some of the squares.
well, I mean, here's a sum of squares right here, right?
Yeah.
These are sums of squares, fine. But to get your approximate F statistic, it doesn't do anything for me. So yeah, we disagree on it. We can go on. This is a good debate to have. Maybe we should have it. Maybe we should form a debate about this. The use of sums of squares in statistics, and let's the two of us sit in a room and debate this.
We can. For instance, in meta-analysis, all our Q tests have sum of the squares, and these all special cases of mixed models.
Yeah, there are equivalence classes with it.
Yeah.
But apart from this, when you switch. So let me put it this way: the sums of squares are for a very narrow. If you think of the universe of models that are out there, sums of squares apply to a very narrow window of them.
I agree with that.
Right. And so.
See, the point I'm making, if you want to understand the epistemology of your models,
Right. No.
you can go back.
I don't care about the epistemology.
See,
I care about
I
the.
do. I read the old stat books.
I mean, those are good. I agree. I think those are good. There's some value to some of that. But I think the reality of it is, if you're trying to educate people with sums of squares,
You have limitations, no question about it.
that's fair enough. Okay. So I'm not allowed to touch sums of squares.
Oh, no,
I can touch some scores, but sums of squares, screw that.
If we will agree that they are not practically useful, I will argue that they are theoretically useful for understanding.
Yeah, so that doesn't go away, right? I can hear you on that, definitely. I mean, but at some point they all go away. By the way, if anybody's looking at what I have here, this is the ProcMix user guide, which is a wonderful way of looking at mixed models. Studying this was hard for me. It was my hobby after I left grad school. Now I'm like, oh, I love it. Yeah, clearly that's it.
Say, aren't you guys glad I don't do it this way?
But if you wanted to come up with, for instance, where you would look at a sum of squares table to figure out what your F test was for a certain effect, either fixed or random in this case, here's how you do it, right? You don't see sums of squares obviously there, although if you unpack a little bit more, the sums of squares that you would typically find for the fixed effects show up. Right.
And when I approach mixed models in classes, I don't go back to some of the squares either.
All right, that's what I was going to say, all right.
For the practical aspect, they don't need that.
That's right.
Now, in my mind, if you really want to understand the epistemology of the models, you need to dig on them.
Yeah, I don't care about that. But I'm talking about the dogma that comes from these. If you read the articles from the back of it, anyway, well, we can disagree, and I'm happy to do that. In fact, let's have a debate about it. But I don't even know that we actually disagree. We're sort of just coming up with philosophy of things. I would think that I was going to rip on the sum score, so let me just do that real quick.
Sure.
What's wrong with a sum score?
You're assuming every item counts the same for your linked pair.
That could be it. Or is that bad? Oh, man, those of you who want, I want to debate here. Come on, debate me. Is it bad to sum up items? Not necessarily. But what are you assuming when you do?
Equal weights.
What's that?
Equal weights.
Equal weights.
Dimensionality.
Dimensionality.
Local independence.
Yeah. Do you check? Are you able to check any of that with the way that you add things up?
That's what
Here's where I'm stuck. Not stuck, but I've had some great conversations with some of the colleagues here. You can show through, even in days here, or through these models, that there are equivalence classes where you can come up with a psychometric model that equals a sum score. Right? So if you take a CFA model, where the latent variable estimate equals the sum score. Right? So if you take a CFA model and you fix every loading to be equal and every unique variance to be equal, this is what we would call a parallel items model. It's the foundation where Spearman-Brown prophecy formula, Spearman-Brown reliability, came from 1919, right? If you do that and you output the EAP estimate of your latent factor, the correlation of that estimate with your sum score is 1. It's not less than 1, it's 1. So, question I have then, the hard part, I don't think I can easily say yet, I haven't found the logic, I haven't thought that long about it. But if you have those two cases, right, if you can say, over here I'm just going to add things up and I'm going to do this classical test theory where I imagine the sum of infinite tests and the true score and error and all this, the fun things that you learn about. And over here I'm going to go put this really restrictive model together. I'm going to end up with the same score for people. What I really want the connection to be is this model and this model, this side and this side have a link, and I haven't been able to logically establish that yet, but maybe maybe you know how to do that, right? Because if you put it in that framework, now all of a sudden, what is wrong with the parallel items model?
It probably doesn't fit.
Yeah, that's interesting.
Right?
Yeah.
Or if you want to go a step further, the same thing is true of a Roche model. You fit a Roche model and you sum it to its binary items, and you sum of the items themselves and spit out the EAP estimate of the score. The correlation is 1. That's a tough thing to understand, right? So when I hear it that way, when I have that piece of information, the missing link is the combo, right? The classical test theory idea versus the model idea. But I think that link can be established. I haven't put down the prepositions, that the logic that flows with it. Then all of a sudden, we put it in a framework that we can actually evaluate a little bit more interestingly. That's important.
Even if that link does exist, they are different philosophically, right? Because with classical test theory, you can't disprove the assumptions with data. At least with a model, with constrictive, you can check model fit, which is something we would like to do.
Right.
Classical test theory is kind of believe like, seems reasonable, let's roll with it. And so that doesn't sit super well with me.
What's that? The same or not the same?
Just classical test theory in general.
It doesn't sit with it. I'm okay with. Yeah, I don't want to. It doesn't sit well with me. That's clearly my bias. But so think about that. Why I'm saying this now is because our program the EMS program seems to spend a lot of time on adding things up. And I look at that and I'm thinking, did you hear this link before with the test score? Do you want to see it? I mean, do you want me to code it for you? I have some examples from my last SEM class where I show this as well, if you'd like to go through my notes online to see it for yourself and try it and play with it. By the way, I thought it was different. So when I took, first of all, I've never taken a classical test theory class. I know, crazy, right? But neither did Bob Brennan, I understand, so we're okay. But I'm just joking. I learned what I know about. I mean, I clearly have studied. I've read books. I've done work on my own. But where I got into my first latent variable class was Roderick McDonald, and it was with this unified test theory treatment where he said, "Well, there's classical test theory, and we're going to do the same thing with factor analysis." So that's why my head was biased in that direction. It was the first thing I learned about it, right? We sum things up, and we go and then use coefficient alpha for reliability, right? Coefficient alpha, do you remember the type of model it assumes? It's not parallel items, it's tau equivalent items, right? Which in the factor analysis analog would mean loading or unique variances vary, loadings are equal, right? So I assumed when I was trying to go and do this lecture a couple years ago, I need a tau equivalent model to go come up with a sum score to see if they were the same. No, it was actually the parallel items. Isn't that interesting? So the parallel items gives you a sum score, it gives you the factor score and sum score correlation, and a reliability that we think, that can't possibly be accurate. We need to go and weaken the assumption of parallel items, make it tau equivalent, use coefficient alpha, or whatever we want to call it, And when we use coefficient alpha, sure enough, if you look at the latent variables, they're highly correlated with the sum score, but there's some reversal to it, like meaning you change the order of people a little bit. That's bothersome to me as well, right? And the fact that I didn't know that when I was going to build this lecture was really, really, when I told Lisa, she's like, what? Right? This was sort of common knowledge, I thought. Oh, well, we summarize the sum score with alpha. Reliability, right?
That's
Anyway.
the first mistake.
I know. So anyway,
Use alpha.
where am I going with this? I jumped off a cliff. Dogma. Don't always assume because the epistemology is there that it was right to begin with. Science is self-correcting, and it's been a process that we've gone along with. That's where I'm going with. So, all right. Other thoughts or questions? Have I scared you all? Wasted a whole half hour? Good. Let's get to class. We're running out of time in the semester. Everybody's happy. Never mind. Lisa's not happy. Did I say something bad? Okay. Okay. Shall we get to this week's lecture? We're going to get into polytomous categorical data this week. Yippee. So, I noticed I got dyslexic about the date. It's not April 92nd, 2019. It's the 29th of April. So I have a few slides that you said that sort of helped last time to have slides and R. We'll see if this works the same.
Just quick side question: how do you create an RPrez?
If
Pretty slick.
Yeah, if you go up to the File menu and under New File, there's an R presentation. And it's like a unique RStudio thing. I'd avoided it before because it's like uniquely RStudio, it felt like. But it seems to work just fine in if I'm going to be in RStudio already, it seems to be a nice deal for it. I don't have a lot of slides. I'll just put it that way. Can I give you some backstory about this lecture? I was like, Tuesday, I'm going to work from home. I'm going to get this lecture done. I'm going to knock this out in like 3-4 hours. 3-4 hours later, I had run one of the models. One. I had spent hours on message boards trying to figure out errors I had. I had been banging my head against the wall. So much so that when Lisa came back on Tuesday, I was like, I'm glad I got 3 models done today. 3! This is like a 12-hour lecture that has like hardly anything in it, I feel like. But what I want my experience to do for you is to warn you about this, to try to not repeat my mistakes as much as I could learn. I mean, part of it's my own thing. I start not being able to get the right answer, and I'm like, come on, this should be simple. What is it? I stripped a model down to like nothing. Like it was just one categorical variable with like 3 categories, and it still blew up. And I'm like, what is going on here, right? So then I start freaking out.
Class cancel.
I thought that. I'm like, no, you can't cancel class over this. You have to have like cold or snow in Iowa to make that happen. Not like I couldn't get the program to work, right? That's BS. All right, polytomous categorical data. The idea is this: we're going to have countably many categories. Say countably many, a handful usually or less. Countably many makes it sound nice, right?
Countably many could be infinite.
Just one less than infinite, right?
No,
it can be?
Yeah, the integers are countable.
I didn't realize that. So Poisson, the range of Poisson would not be that.
Right.
Okay, so this is a finite number of categories, typically a very small number of categories. Discrete data, though. So we're going to take the example for this is going to be that conspiracy data that we had before that we ran CFA, and we're going to do a comparison of CFA and IRT, which I found exciting. Maybe you won't. But this is it. What is the distribution of the data? What is the likelihood function when you have a handful of categories?
Compound binomial?
Could be. There's a lot of different ways you could go. If you go into the case of the IRT models, like rate of response, partial credit, nominal response, which are the models that I have right here today, they're all multinomial. Or another way of calling it, a multinomial is an interesting distribution. If you think of it, if we had n observations total, and they all could take one of C categories, then X would be the count of those in each. X1 is the count of the observations in category 1. Think of it like with 6-sided die. We roll the die 10 times. There would be 6 categories. X would be the count of the number of times we observed the number of dots, the number on the die, and would be 10. So its general multinomial function looks like this. All right, and this is the PDF for it. Which is fine until you want to do like IRT and you're like, I have one observation per person usually, right? What does that boil down to? It becomes a much, much simpler. With one observation per person, really we're talking about one observation. That means one of these x's will be 1, the rest will be 0. So this likelihood function simplifies to being there's a probability for each of those categories. They sum to 1. I didn't add that constraint in the previous slide, it's not here. And then that probability for the distribution is what happens, right? So for the 6-sided die, each of these probabilities is equal. It's 1 over 6. When we roll the die, what's the probability we get a 3? Oh, that's the third one. 1/6, right? And so what the model is going to do for us for each of these, so that's sort of the big picture. The most general case we could come up with is some type of model that models each of those probabilities themselves. What typically happens in our way of organizing the IRT models is we sort of layer them in nested order. There's a great paper by Thyssen and Steinberg in the 1980s that talks about polytomous models. It's cited, I mean, all the time still. 1986, Lynn Steinberg. She was a KU student, like Lisa, but not like Lisa. You have a KU PhD. You don't want to talk about that? Never mind. All right, so the greater response model. Let's do some greater response. Let's get into this. The probability that X for a person and item is equal to some category, right? That's like saying that X sub C is 1, given a potentially multivariate set of thetas. The way that we phrase a graded response model is through a difference in cumulative logits, and I always get the order mixed up when I'm talking, so expect that coming. Right? F this up. I have a perfect streak of getting it backwards, which make you think I should just flip my mind, but I can't flip my mind that easy. Right.
So, my wife likes to put the toilet paper and the paper towels on backwards from what I expect, and she's like, I'm just doing it randomly, I just don't even think about it. I'm like, no, every single time it's backwards, that's not random. Or it's very unlikely to be random.
It's like I've coded things before and I had like the probability to have the converse of the number I was expecting. So I'll just take 1 minus it to fix it and move forward. Like, yeah, clearly there's something wrong in it, but it's coming out to be right, non-randomly, right? Or sorry, non-randomly wrong, so I can just non-randomly make it right. Did I do something wrong here?
No. Let me ask you a question, but don't let me get you out of this. It's a yes or no answer. Have anybody tried to map these models to ordinal regression?
It is the same.
Because I'm looking at
It's identical.
It looks like exactly the same.
It's an ordinal regression model, but we just didn't observe the predictor.
Okay, thank you.
Yeah, partial credit is adjacent category logit.
I was going to ask you that, if which one of it, thank you. That made me feel so much comfortable.
Yeah, this, by the way, this is how I approach all latent variable models, is I think of what happens if theta or the latent variable was observed. And I go find that model first,
Yeah.
and I go read it, and then I go back and I read this. Because it simplifies a lot of latent variable world when you do that.
Yeah, for me, give me a point of reference and something that I'm familiar, so then I can go back.
So, greater response, I tell you, I get the order wrong a lot. When I get to partial credit, I screw that whole thing up, so I'm just going to warn you right now, I'm not a partial credit expert. Partial credit, my score on a partial credit item for partial credit models would be 0. I haven't gotten above that to get partial credit yet, but I'm still going to try, right? So here's how we do this. We form these two item response probabilities. Basically, this probability right here, the probability that X is greater than or equal to some category, And that is where we put our familiar IRT form. And again, everything I talked about last week, probe it versus logit, that would change sort of the kernel of this thing, or whatever it encapsulates it, the inverse length function of it. Also, discrimination difficulty. I had made this a multidimensional look here. We're only going to use unidimensional models today. In the multidimensional models, you typically find the slope-intercept form. For the unidimensional models we're going to do today, we're actually going to do discrimination difficulty. And we're going to do that because I had multimodality that I couldn't solve otherwise. And so I was able to fix things. So, questions, comments? All right, let's go model. In our file here, we're going to find that we have, there we go, just run some things. Our today's example, this is our 10-point, our conspiracy theory data, which isn't great data, but I love it, so we'll go with that. And read in the data. I tried to make a nice, a nice plot, although I didn't get it here. We're going to do, to start with this, pardon me, we're going to pull out the unidimensional CFA model from lecture 9 first. Remember that? Lecture 9 took us like a month, but it was good. I was stalling for time. Keep looking at the clock. I was stalling. I only learned from the best, which is my son. Anyway, basically here, remember how fun it was to have our data be denormed? We're not going to denorm them. We're actually going to decat them. That's the distribution. And actually, let me just show that to you real quick. I have it over here. It's the decat function. Decat expects Y to be categorical. It tries to order those categories, and then what it will do is, with this probability pi, you should have one probability for every category. And it notes that the nice thing about the probability mass function is it does a sort of a self-normalization of pi, so you could actually give it something that's not normalized, meaning it doesn't sum to 1. I don't like doing it that way because I want to make sure I have my model right. There's a lot of ways that you can screw up a model when you don't see that, but if you're really confident in what you're doing, it makes it a little bit quicker. So you don't have to give it a vector. It'll go and normalize the vector it gives you for it. Okay, but that's that. So we can run, here's our date code. By the way, I put this all into the R2JAGS framework, and we're going to run this with our parallel R version of it. And that ran pretty quick. 4 chains, 5,000. I used a 5,000 iteration chain, 3,000 burn-in. Convergence occurred. By the way, I made this using not the marker item. Actually, did I do the marker item here? Yeah, I did. I did not do. I standardized the factor for comparison's sake to try to make the scale the same. So our latent variable is this. Now note, I used a truncated normal. I figured out how to make it work. One of the nice benefits of being on message boards for hours, if you're using R2JAGS, it doesn't like, if you have to put a semicolon after the denorm to put this truncation function. Basically this says, truncate this distribution, and in the parentheses you give it the lower limit and the upper limit. And if you miss one of those, it says the lower bound is whatever is assumed by the distribution. Right, so this says, I want lambda to be positive. I want it to be above 0.
Can you do folded distributions in the same way?
Folded, I mean,
you know how in the truncated you get rid of the negative part.
Right.
And in the folded you will have the negative part and basically convert it to positive and fold it on.
Yeah, I don't know how it works. I think effectively it will be folded. It'll basically take the mass on the negative and just put it over to the positive, but I don't know exactly.
Okay.
So, I'm sorry, I don't know exactly.
Yeah, you made me think about that.
Yeah, I think it is. I think it is positive. I think it is. It adjusts the probability mass so that it's appropriate for it. So, or the distribution mass. So that's the one catch with this. I wanted to standardize it because I want to compare this really quickly. Here were our results. Factor loadings with the means. EAP estimates of factor loadings, item intercepts, unique variances, factor scores. And we have our DIC. Sound good? We also have the beautiful model fit using posterior predictive model checks. Again, here's the example. I took the looking at the correlation between items 1 and 2, and I compared that with this posterior distribution. But really, what I want to show this is the number of items where correlations are in the tails of that posterior predictive distribution. It numbers 13 items here. You can see the percentile rank for most of these, right? So there's our model misfit. Any questions? All right. So now let's go to where I thought, I sort of said this the last time. My bias with this is, why would you ever do CFA with Likert data? It doesn't seem to make sense. The reality of it was, if you're not in a Bayesian framework, it's really hard to get a lot of the categorical models for data to work, particularly for sample sizes like we have here, 177 items. A lot of times it's because those multiple intercept parameters. So if I go, I don't need to flip back, but if I go look at our model here, you'll note that this intercept, or this right here, there's one for each category but one. And so if you observe an item response that has a limited number of people in a category, typically what happens is that intercept has a hard time being found estimation-wise. In a likelihood sense, when you're trying to optimize the likelihood function, that corresponds to this being a very flat part of the likelihood function, so it has a hard time figuring out what the peak is. But in a Bayes sense, we can take that likelihood and make it less flat, because we're searching the posterior, by putting a prior on it. So that prior distribution can help sort of give us a little bit more of a space for it to be found. That doesn't mean it's stable. It doesn't mean that it's going to work long term, but if you have a limited sample size, it works. So I think the reality of it is, I may say, if you do Bayes, there's no reason to do CFA for Likert data. I mean that, because you're already jumping into the Bayes pool or whatever. But if you're not doing Bayes, it's still pretty hard, I think, to make it work. Wouldn't you say so?
The intercepts can be found in the sense that there's data that goes into them. Like, you know what proportion people fell into each category. It's the loading, I think, would have a harder time being estimated if you were fitting a model in which you had different loadings for each submodel.
That is possible. If you
strain is what makes this work.
I'm saying intercept because when I output like the gradient information for my ML, I typically find gradients for intercepts to be really, really high for limited data. I feel like that's why it seems to be having a problem. Yeah.
Actually, in reality, what I did is, if, for example, one item has 7 categories, one category, for example, category 1 has small sample size. Can I just group?
You usually, yeah, that's what happens. You combine it with another category, but that's harder in a generalization sense. But yeah, that's to make the model run. You would do that. Here in Bayes, we don't have to do that. That's kind of what we're saying. It's sort of a trick one way or the other. You tighten a prior. Is that more realistic to data versus combining a category? I don't know. I like that better. I don't like playing with my data.
If you're combining categories, why don't you just have those categories originally?
Exactly.
To combine.
Long story short, I found these types of models to be really hard with observed data in a non-Bayes sense, particularly when we get to nominal response. That one is really tricky to make work. Mm-hmm. No, that is the slopes, yes. Okay, so here's the unidimensional graded response model with a normal ogive. We're going to start in the middle of this syntax right here. The person and item, our data is X still, but we're going to say this follows D cat, that distribution I just showed you before, and we have to give it a probability. And so I'm giving it a 3-dimensional array. So this means for each person and item, they're going to have 1 to the number of categories for the item. This is a piece of data I'm going to input into JAGS, which is a vector of how many categories for each item. But they're going to have probabilities for 1 to that. That's what is expected. And all the code above it is to make the greater response model happy. To make those probabilities in line with what the greater response model thinks they should be. Questions? Yes.
Is it possible to use different specification, not using DCAT, where like
Yes.
like Dirichlet? Is it any
Dirichlet won't work here, mainly because it's hard to map the Dirichlet on. You can't easily map a latent variable into the probability for Dirichlet. You may be able to make it work. I haven't seen it done as much. It's not the same as the greater response.
I only I saw mixed IRT models.
Now mixed, yes.
So, but I was wondering why they use that,
Ah,
not
so in mixture IRT models, they still will use this for the data within class. But we're going to talk about this next week. There's for the latent variable, for one of the latent variables, the categorical latent variable, there's a number of classes with it, and you have to estimate the probabilities with it. That's a Dirichlet. That's actually a conjugate prior for a multinomial distribution. But for us, because we have a categorical data, and we're going to go and do an IRT model that hits the data, there's not a conjugate prior that works for it. But we will talk about Dirichlet next week, though. It's a very good question. Back to that, I said there are other things you can put here. In the latest version of JAGS, I couldn't get an example to work, but there's a de-ordered logistic function that's supposed to make this part easier. I could not find an example. That doesn't mean I looked very thoroughly. I wanted to get this running. But that de-ordered logit may simplify some of your syntax above it. But only in this case for the greater response. It was just an ordered logit. When we switch to partial credit, or when we switch to nominal, we still need this, so I just ran with this time. Other questions? Okay. So what are these probabilities? Now that's where the greater response model comes in. This first part up here, I'm going to form the cumulative probabilities. Right? So I'm going to say the very first, the probability that someone answers with a 1, the item responses here are 1, 2, 3, 4, 5, so conveniently they're the same as the number for the index. The probability they're at a 1 or higher has to be 1, right? They answered somewhere on the scale. And then for the remaining of these, I created the item response function, the C prob means cumulative probability, where I took the discrimination difficulty coded IRT model that's been put into a probit. So phi is the probit function, with a loading that's common across all the categories, a theta for a person, and now B has number of categories minus 1 numbers. So when I start with category 2, I'm really using the first B for it. Now this is not identical to the coding that I showed you in the slides, because the discrimination difficulty, the B and the mu don't map on to, they're not identical, but this is a way of doing it. So what this is doing though, is it's saying that each one of these cumulative logits, B would be the value of theta, where it would be a 50-50 chance you're at that level or higher for the score. Are we good with that? I always like this better in describing what's going on with the greater response anyway. Our slope retains a similar meaning. It's effectively the slope of the tangent line at that point. And if you look at the cumulative logit graphs, or in this case cumulative probit graphs, the OJAGs, they're parallel because it's common slope. So it's cumulative. What's that?
Proportional odds.
Proportional odds.
Translating.
That's good. So after that, we go down here. We build the not cumulative. We build just the probability by taking, for the first, all but the last category, the value of that category minus the one above it, cat plus 1 here. And in the last category, we just assign that probability itself, and then we run this. That seems pretty straightforward, right? It should work. That, by the way, took the 4 hours. Let me go through the rest of the code and I'll tell you why. Actually, the reason why is this, as Martin Plummer wrote in a blog post, it's a little curious behavior or maybe a bit unexpected behavior. But when things get if you have a probability that's equal to 0 for one of these, you can't have any data in that spot. So if, for instance, you have 0 probability for category 2, and all of a sudden the first response is a 2, it says invalid data X parent, or X child doesn't match parent or something. So just nonsense BS error good, right? Which is nonsense only because I don't know the inner workings of the program as much, right? But something that was like, oh, dude, I have a 0 probability and it can't be a 0 probability, right? Well, it turns out when JAGS initializes a lot of these parameters, it initializes all the probabilities at 0, unless you specify values for initialization. Now, Martin Plummer on a blog post maybe a year or 2 ago said, by version 5, he hopes to have that changed. But that took me hours to figure out. So I had to go and figure out how to get initial values in. And once you get the initial, so the point is, when you're doing a DCAT, you almost always have to specify initial values, because there's a step before it does the initialization with the priors, where I think it does a data check, and it's like, hey, you've got zeros here. You can't have numbers over here, which is really ridiculous.
It seems weird that JAGS would initialize it at 0 for probability.
A bit unexpected, I believe, is what he said, which I think he's from the UK, which would probably mean very unexpected. This class is a bit of a clusterfuck. Sorry. Maybe they wouldn't say that.
And this assumes that you have responses in all the categories, right?
Yes, that's also true.
So
If you don't,
would you have to manually sort of say, for this item, I only have 4 options that were used?
yeah, I think so. I didn't have this problem with the data, but I didn't want. By the time I figured this out, I was so frustrated that I was drinking. It was 10:30 in the morning. I found some heroin. I was like, no, never mind. I shouldn't say that. Okay, that's a joke. That was sarcasm. But yeah, I think you have to. Sorry, internet. University of Iowa's killing it. So prior distribution for the factor again. So I was going to do the other part that was frustrating. So once I got that solved, I allowed, my preference is to marker item the thing, because we're going to have to do that for general, for the, the multivariate case. And I tried doing that, and I had multimodality, the non-convergence. And so I was tightening the priors. It's like, forget it. I'm so frustrated. We're all doing A and B. I can describe what's happening in greater response better in A and B anyway. Boom. So I just made theta standardized. And then for each of my categories, my A's follow a truncated normal also. This is to correspond to the factor analysis from before. And my B's here, now this is the other part that's excessively frustrating about JAGS. This truncated syntax seems really awesome, right? You can go and truncate things. You can even put variable names in there, but when I coded it up with B's, it gave me, I have a graph that has a cycle in it. You can't do that. And so I probably could have shortcutted this B star. I found some kludgy syntax. I say kludgy because it just doesn't sit well with me. But what we're going to do is generate 4 B values. Remember the B's, the other part, I didn't say this in my slides, although it does mention that B's have to be ordered to make the greater response model work. I started with syntax where I would order them based on the values of other B's, and it didn't like that. I probably could have switched to what I've done here, but I didn't end up. So I'm generating a B value called B star. That's really the thing that's being drawn. I'm generating 4 unordered normal variables. And then I'm switching it with the sort function. There's a sort function that sorts from lowest to highest. And by the way, this is the other reason I went slope-intercept. I went from slope-intercept because the order function. Remember the b is equal to -1 times. The mu is equal to -1 times a times b. So the order for b is reversed for the order for mu, right? This only gives us one order, and it fit with b, so I stuck with it. All right? Frustrating. So it's generating 4 unordered b's called b star, because they're spectacular, I guess. And then they orders it into b, and then b gets used in the length. It's a really complicated step, right? So think about it this way. It's like I'm going to draw a b star, I'm going to sort it, put it into b, and then it's going to go up to the top and go through all this syntax here to express b as probability, and then go and put it to data.
So what I wasn't following your sorting code there. So you've got B star calls item and cap. So item 1, category 1 is going to pull for that. But how does the sort function ensure that the B star pulled for item 1, category 1 corresponds to the first category of?
So what happens when in JAGs, the thing that is driving me nuts also is that you have to express the limits of the vector. And so what it's doing here is this is 1 colon, and this would be 1 minus, or the number of categories minus 1.
1 through, yeah.
Yeah, so what it's doing is effectively saying, I'm going to give it B star. It's going to have, for all these items with 5 categories, there's 4 of them. It's going to take those 4 on input, sort them from lowest to highest.
And then assign them?
And then assign them
Gotcha.
in that order.
So really the cat and the B star above doesn't really matter. Just saying, hey, give me 4 of these. I'll sort the 4 and assign the lowest one to the first category. I got you.
That's exactly it. Yep.
I
Yes.
think I used the T function.
Yes, I tried the T function. So here's the other part. If you're using Winbug, I tried the T function with it, with the limits for B, and it didn't like that.
Actually, I used the whole syntax to be text.
Text.
Yes. So.
But even with that, even with the T, when I tried the text actually on this as well, it told me I had a cycle. Because what ended up happening was, if you put the B values in different places, it all of a sudden thinks B depends on the value of the other one before it. And so in the graph, it starts building a graph where I may have done something wrong with my syntax. That may be the case. I'm not ruling that out. But I also saw other people online having to do this as well. Whereas in Winbugs, where they had an I instead of a T, it seemed like that didn't trigger the cycle like it did for me. But you may have done it. If you send me your syntax, I'd love to see it so I can try to add it in. I don't like this code. I really don't. It drives me nuts. But, okay, so big catch when you're doing this yourself. Several big catches. The first one is initialize the parameters. And I'll show you how to do that in just a moment. The second one is the B ordering is problematic. Questions, comments, thoughts? All right, let's talk about initialization. So the initialization comes in this set of code right here. I'm going to run line by line. These are just setting the priors for each of these. By the way, my prior variance for B and A is 100. So my prior precision is 1 over that. I load up the data. Now the initialization function using the R2JAGS package, you can provide a list of it. This was really hard for me to get as well. But this function, what happens with this function is very interesting. I had to go into the code to figure it out, but when you create a function like this, if you call the function yourself, you'll see some output. This is what it's giving you. So really what's happening behind the scenes in R is the R2JAGS package is calling this function, which is really going in and it's, I said effectively do this. Randomly give me a uniform distribution for 10 A's, so there's my 10 A parameters, one for every item. And then for the B parameters, I just set them in order rather than randomly do it. I could have done differently with randoms, but I decided to keep it this way. This B this is the B matrix that JAGS is going to be working with when it gets input. So anything you do when you recognize when you're giving it starting values, you have to understand the size of these matrices that's going in. And where this becomes an issue is when you start to have constraints. So in rate of response and a nominal response, we have to put any constraints on B. And you may have a matrix where you have like the first column or the last column is not being used, usually the first column, otherwise you just shrink it. And then that's where you put NAs. That also took a long time to figure out. But I'll show you the syntax for it coming up here. This made me almost rethink my decision to like Bayes. I think I was rationally angry, not irrationally angry. So I ran my syntax. So we run this we have 2 minutes before break. Let's make this thing charge forward. It takes longer than the CFA code. I'll warn you about that. It doesn't take tremendous amounts of time. Maybe it's enough to get through a first minute or two of a song with your, in my program, it will play music for you. You'll know I've made it when ... It's still thinking about it. Anyway, why it's taking long. There's multiple reasons why. The primary reason is there's no conjugate prior for what we're doing. The secondary reason is there's a bunch of loops within this program that it takes a while for it to execute. So you put those together and you've got code that takes a while. But while this is happening, should we start our break? All right. Let's take 10 minutes, breathe a little bit, leave the hate behind. Actually, let me do the hating. Hated on sums of squares today, hated on sum scores. What else should I hate on? Anyway, I'll stop. 10 minutes and we'll come back and we'll resume the fun.